Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So good morning, everybody. I'm Judith Bishop, and I'm chairing this next session of Cloud Futures. We're delighted to introduce here Antonio Sisternino, and he's going to be giving the paper for himself and his colleague Marco Mura on managing cloud infrastructure. They come from the University of Pisa, and welcome to them.
Thank you. So today I'm going to give you a brief introduction to a system we are working on in Pisa. It's called Octopus. It is about mostly managing virtual machines. So it's not strictly on cloud, but more on how to manage the huge data centers we heard about in the last presentation today and also yesterday. So virtualization is quickly becoming a key element in computing infrastructure because it allows for many reasons. One of them is you can better use your hardware. If you have one server, you can partition your services into different operating systems. You can achieve better usage of your CPU cycles, and so you're going to be more efficient with respect to energy. So Octopus is born from a collaboration with Ferrari Racing Division, and the idea is how to manage a cluster of virtual machines in an efficient way. So what is about cloud? Cloud is about data. Data is a really important aspect. There is services. You run services on cloud. It is about heterogeneous systems, especially if you run private clouds, because it should be expected to have heterogeneous hardware over time. And reliability, which is important, because if you buy services from a service provider, you must be reliable. It's about computing center. So many of these things are suitable for virtualization. And as Dan Reed told us this morning, virtualization is often viable. So we have very powerful computer systems that gives us more horsepower than often is needed. So that's fine. And let's start with a demo. I know that this is pretty much unusual, but it's difficult also to define what Octopus is. So Octopus is something like this. So this is a cluster on our IT systems facilities in Pisa, and it is an HP blade system with 8 blades, so 32 cores, and so we're able to run up to 32 virtual machines on top of that. Each node has 8 gig of RAM. It's a fairly available cluster. So I log on into the system, let's say using my account. Oops. And what I get is my virtual machines. So the idea is that users get access to their own virtual machine and they are able to manage them from the web. So I can go here and say, new, I want a Linux box with 1 core and 1 gig of RAM called hello, and the machine name is full. and the password is QWERTY. I'm gonna remove this. So what's going on? Now we are running on a distributed network of hypervisors running Microsoft Hyper-V server. And we're able to interact programmatically with the Hyper-V infrastructure and allocate virtual machine dynamically on nodes. So here I was having two already created virtual machine, and here there is a third one, which is the one I've just created. So under the hood here, the operating system is booting. At the end of the boot, the image is configured so that it integrates with the Octopus database management. So actually it gets into all the data you need for managing the virtual machine. And that's it. And so every user in this way has access to his virtual machine and can suspend a virtual machine, like I'm doing with this Win7 box. And I can stop, so unplug the power, and I can migrate the virtual machine. So actually this migration is more a test, because one of the features of the system is that virtual machines are running on a cloud, because you don't know really where the virtual machine is running. So actually when I click this button, which is used for us for testing, the virtual machine gets moved lively onto another node. And this is very important for several reasons, mostly management reasons, because it allows sysadmins to move virtual machine around and have access to the physical hardware without interrupting the services. Moreover, you can also pack computations into single nodes and shut down unused nodes. So you can also be more greener in your power management. As you can see here, we're able to get the screenshot of the. So. Oh. Okay, something. However, this is the small one. This is the screenshot of the running virtual machine. So actually these three dots are the login of Ubuntu server, and as it is here for this one. And this virtual machine now is up and running, so you can access. Okay, this is the screenshot, and if I go back, refresh the list of machines, I can obtain the IP address of my newly created virtual machine. And I can log into it. So, okay. So now I can run as my username, not tab. And now I can QWERTY. Okay, QWERTY. There we go. So this is a brand new virtual machine that has been created on the fly, and it's fairly useful because if you have to run a lot of computation, you can install images easily with this stuff. And at the end of the day, you can decide to turn it off. Oh, yes, I want. And delete the virtual machine. So recover all the computing resources needed from the virtual machine. So I'm going to unplug and turn off the machine and delete it. Okay, so this is what Octopus is about. So a nice thing is that actually we've been able to, all the interface you saw that has been inspired by Windows Phone 7 series that has been about to be released, is working on a standard browser. So you can have also access and monitor your virtual machine from a standard server phone. and you have access to all the information you need. Okay. So what is the architecture of the system? So the system has a number of storages. A number of storages here that can be single PCs or whatever. You can have many more of them, not just one. So usually it's up to you to decide your own architecture. You can use spare desktops or whatever. And then you have the computing power, which is provided by, I don't know, one unit arrays, desktops, or better infrastructures, blades. And the Octopus simply is a software that coordinates resources. So actually, all the software we are using are it's production quality. I mean, it's Hyper-V, Microsoft Hyper-V 2008 server, and we've been able to use all the services you get from it. Okay, so the software, the infrastructure has been realized using Windows Server Hypervisor 2008, Windows Active Directory, and the Octopus services that we have developed. And as for the guest operating systems, we have integrated with the system, which means mostly you have to do a last step at the end of the configuration of the system to integrate with the Octopus server, gets your IP and everything. And we've been able to run Linux, which is supported by Hyper-V, Win 7, which has been really appreciated because we're starting to run our administration offices on a virtualized boxes. And Windows Server 2008, and we've recently upgraded to Windows HPC services. So we've been able to use the Windows HPC scheduler to schedule computation on virtual machine using this. So what is the structure of the system? So the system is mostly built on top of standard interfaces. So these are robust and everything. So the WMI Hyper-V calls, which are available, shared storage interfaces, and DHP and networking and DNS. So actually, if you have the Windows DNS, you can use calls to configure nodes on the fly and have publicly available virtual machines. We are also using the tunneling facilities to tunnel remote desktops and SSH facilities into a private network. But anyway, most of this is up to the sysadmin that decides the configuration. Then there is this HyperF library, which is available on Codeplex, which has been a port of the WMI calls on top of F#. So actually, everything has been implemented using the F# language. And using this HyperF, you're able to migrate lively. You can even do a hard checkpoint of a running virtual machine. So if you have a really long-term jobs running, you can hard checkpoint them with an overhead which is around 1 minute. And then on top of that, there is the Octopus system, which is an interface that you've seen that is web-based and tries to convey the idea that managing the resources should be easy, not with a sysadmin that assigns nodes manually and everything. So we're ready to try to do better. And what about? So we relied upon a really nice feature of Hyper-V, which is differentiating disks. So using this approach, we've been able to pack into a single image many images, because you can build a disk on top of another disk on a sort of copy on write. So the newly virtual machines created requires only the few bits for the operating system to start and create all the paging file and small differences on the base image that stays the same for all. So actually, Windows Server 2008 instance costs us around 400 megabytes. And since differentiating disk can be layered, so you can build a differentiating disk on top of another differentiating disk, we're able also to do snapshotting. So actually, if you have a virtual machine and you want to try something on that machine, you can do a snapshot, have a new instance, which is the photography of the current running machine, do whatever you want, and backtrack if you're not satisfied with the changes you've done. So this is a really old refrain that comes from the Lisp community, mostly, which says as memory management is too important to be left to programmers. Memory versus, this is a versus, memory management is too important to be left to the system. So C programmers were against system automatic memory management. Lisp programmers were against human memory management. At the end of the day, we can say that mostly now we have most garbage collecting, so automatic memory management. And this is the same, I think, for virtual machines management, system management, because as the number grows, humans tend to be fault error prone when they manage large numbers of objects. So we need systems that takes care and schedule resources for us. So management is important, and actually Octopus features 3 interfaces. So the web one you just saw, and sysadmin which will be a web interface, and the last one, and F#, sorry, because since everything has been implemented in F#, you can use F# interactive, which allows you to interactively call F# functions, so manage your virtual machines in a sort of shell. And then you have programs using F#. So actually, you can manage and schedule your virtual machine as much as you like. I mean, it's up to you to decide the best way to do it. So we're still working on Octopus, and the next step, so actually we built the infrastructure, but the next step will be implement a policy manager. So actually we are looking for policies to manage your virtual machines, such as I want that user can instantiate at most 10 virtual machines that runs at most 15 days, and after 15 days they'll be automatically erased, so deleted, and you can recover. Or whenever a non-server virtual machine goes idle, suspend the virtual machine, so you can recover computing cycles. And the action, so these are virtual machine status, user-based policies, and system-based policies are the inputs. And the action you can take are, you can shut down machines, delete machines, move machines across nodes. For instance, for packing computations and be more power efficient. So the scheduler will be the most critical part of this, and we are attempting to implement an intelligent scheduler. I mean, we're trying to implement non-trivial policies and move machines around, not just for fun, but because machines are really expensive. So we recently performed some green computation. We did a nice job in measuring how much energy power requires an algorithm for running. And during these experiments, we ran into a pretty interesting fact. So actually, these are graphs that shows you that the average power absorption, so these are watts, and this is the input of an algorithm, changes depending if you are using 1, 2, 3, or 4 core of a processor. So actually, it turns out that the waste of energy power, if you use just 1 core on a 4-core machine, it's up to 10%. So actually, it's very expensive having virtual machines, having standard machines idling. So until we wait that this wonderful parallel programming take over, we still have to do with a lot of single sequential programming. And virtual machines are a viable way to have many of them running on a quad-core machine, up to 4. And the benefit you're getting is that you're using better your power resources. Okay, so Octopus is a virtual machine scheduler, mostly, which is already, go back, which is mostly product quality because it's just a scheduler. So the virtual machines are accessible through the standard Microsoft interfaces, so you can start using. And in the worst case, you have all the virtual machines and you simply give up in trying to use the system. It mostly eases the management of cloud computing resources because actually, since we got this system up and running, the number of virtual machines we created has been incredible. I mean, I never dreamt to do it manually. But actually, when I do a development, I have a pre-configured image with Visual Studio 2010, and then I create a differentiating disk on top of that, do my development, and turn it off and on, and create a freshly new installed machine whenever I need. And we believe that it may contribute to achieve better usage of computational resources. So with this, I'm done. And the system is actually open source on octopus.codeflex.com if you're interested in it.
So we have time for a couple of questions. Questions? Yes.
Excuse me, how many virtual machines can you manage by system?
How many?
How many virtual machines?
There is no upper bound because actually we use WMI code that allows you to manage remotely a Windows Server hypervisor. So actually, you can instantiate as many host machine as you want, configure them onto the scheduler, and the scheduler simply do remote calls. So it's up to you to dimension the system, but there are no implicit bounds to the number.
About the Azure in UCSD.
Sorry?
The Azure system for managing virtual machine from UCSD. You never heard of that?
No.
Okay. How does this software compare next to VMware? It also has a virtual machine management.
Yeah, I mean, we look at a system like those. So actually, Octopus, the original goal of Octopus was to build the experimentation setup to do smart scheduling for power consumption reasons. So we were interested in laying ground the infrastructure that was programmable.
So the difference with VMware is with your own tool, you can play with it.
Yeah, that's it. So the idea is that actually with few F# call, you can say for each virtual machine do something, and so on.
You cannot do that in VMware?
Not in this way. I mean, we have more access to underlying systems. Thank you.
Okay, so we're going to continue this session, and we're still in Italy. Just down the road from Pisa, we're going to the University of Bologna, and here we have Fabio Pansieri, who's going to tell us about quality of service-aware clouds. Thank you.
Thank you. Good morning. I'm going to report on an exercise, an experimental exercise we are carrying out in my department with a couple of colleagues of mine, actually 2 former students, both of them, of mine, on adding quality of service tools and software within cloud computing environments. This talk is organized this way. I will firstly motivate why we're doing this, and then I'll try to clarify what we mean by quality of service in cloud computing, and in particular, what is the role of the service level agreements in this context, and what is the earlier work on which we base our current research. Then I will illustrate this architecture we propose, and I will eventually tell you about these experimental evaluation results we have come up with, which is what I'm mostly interested in discussing with you. And finally, I will conclude this talk with highlighting some of the future developments that we think are relevant in this particular context. Then, we are all familiar with the notion of cloud computing, particularly after the second day of this meeting. So I will not indulge on discussing what is software as a service or platform as a service or infrastructure as a service notions. What I think is relevant to say is that as cloud computing is essentially what is summarized in this line by Ian Foster and others, that is services delivered on demand to external customers over the internet. I think it's worth stressing that quality of service is becoming a crucial factor for the success of cloud computing providers. If the cloud computing environment does not deliver the expected quality of service, then the reputation of the quality of service of the cloud computing provider can be tarnished, and then there can be, of course, financial losses. So the motivation essentially is that by quality of service in cloud computing environment, we mean compliance to the service level agreements that an application using a platform constructed out of cloud computing resources obtains from that particular infrastructure. So in this context, we usually talk about response time, throughput, error rate, and parameters such as this. But there are non-functional requirements additionally that can be considered in assessing quality of service. And this includes scalability or availability. As far as this particular exercise is concerned, we addressed mostly response time as the quality of service guarantee we wanted to evaluate. And, however, what is worth mentioning again is that to the best of my knowledge, quality of service in cloud computing is not yet sufficiently investigated, although we have noticed, we have observed sort of growing interest in both industrial research communities and academic research communities on this particular issue of QoS provision. So we come from the distributed system community, and the basis of our work relates to a project which recently terminated, which has had to do with providing quality of service support in a distributed computing environment constructed out of clustered application servers. So we try to reuse the approach we had in that project within this new context of cloud computing. In addition, we are looking very carefully at the results that a currently funded project by the European Community called Reservoir is the results that this project is producing. I shall briefly summarize these two projects just to set you in the context. The TAPA's objective was that of developing a family of middleware services that could make Java 2 Enterprise Edition technology QoS aware, that is capable of meeting SLA requirements, as service level agreements. So to this end, what we did was essentially to extend one particular implementation of Java 2 Enterprise Edition, which is called JBoss, which is in open source, with three principal additional services that are a configuration service, a monitoring service, and a load balancing service that are incorporated in this platform. And essentially, they manage the platform dynamically as the load on the platform, on the application hosted on the platform augments. The configuration service enters in action and reconfigures the platform to cope with the augmented load. And when in contrast, when the load diminishes, then resources added to the platform are released. So the effort of this particular architecture is to optimize the use of resources in a distributed computing environment. The same sort of principle we wish to apply it to the cloud computing. And in particular, we do that, well, I shall ignore this, some detail about the Tapas platform. We do that by adding those services to the architecture that has been proposed within the context of the Reservoir project. Reservoir is a project which is currently led by IBM and looks at providing support for cloud federations. In addition, one of the further aims of this project is providing interoperability and business service management. The architecture proposed by Reservoir is that of a system structured in three hierarchical levels of abstraction. A top level known as a service manager, which is responsible for deploying the application on the basis of what they call a service manifest, which is a new version of a service level agreement. And the service manager is implemented on top of what they call a virtual execution environment manager, which is responsible for coordinating the distributed virtual environment virtual execution environment hosts that are basically the various resources deployed on the single nodes in a distributed system, in a distributed environment. At the moment, as far as I know, only the lowest level and the virtual execution environment manager have been implemented. The project is still ongoing. I think will terminate in a couple of years. At least it's due to terminate in a couple of years. Our approach is to extend that architecture to incorporate in the service manager those services that we developed for the Tapas project. That is this middleware that looks after configuring the platform, measuring maintaining, controlling the compliance with the service level agreement established by the application hosted on the platform, and the monitoring of the execution of the application. This architecture here has been evaluated. I mean, we wanted to evaluate this architecture basically and see whether we got it right or wrong. So we examined the architecture our architecture in a scenario which is made out of a pool of. I was looking for a pointer, but I can't find it. No, there isn't. We have assessed the architecture in a scenario in which we have a pool of available and assuming free, not used virtual machines that can be instantiated and executed on demand. Each virtual machine comes up with a fixed quantity of resources, a CPU, RAM, storage, and can execute scalable services on a pay-as-you-go accounting principle, say. In our exercise, what we wanted to do is basically to assess the cost of allocating resources, allocating virtual machines, basically in order to get some indication as to what would be the better configuration and load distribution policies we could deploy in a context such as this one. And in particular, we would like to devise dynamic configuration policies that do not violate the service level agreement. Evaluating our architecture in this scenario has turned out to be quite difficult. On one end, because of the actual complexity of implementing our architecture, which requires some time and some investment that we didn't have available at the moment. in which we went into this exercise. And in addition, we didn't have available infrastructure, a cloud computing infrastructure that we could use for our purposes. So we evaluated our architecture through a simulation exercise. And we implemented our principal services, and using a request generator and a response generator, we obtained some performance results that I will show you in a moment. So basically, this is, as I said, this is an initial exercise that has provided us with these results. We assume that an application is deployed on the platform using some service level agreement that specifies some quality of service requirements. And the agreement, the negotiation, this is what occurs in practice, is that the service level agreement is usually it's usually agreed that it can be violated for a certain percentage of time. So we assume that that percentage is a 5%. So what is called the SLA efficiency equal 95% means that it is acceptable that the SLA be violated for 5% of the time. We also assume that the allocation time of a virtual machine is 2 seconds. This is a very short allocation time. It is reported in the literature, say there is this paper by Sotomayor and others, who report that it can reach even 400 seconds, the allocation time. But as we were not currently interested in designing policies for bootstrapping virtual machines quickly, rather we wanted to see whether we could stick to an SLA as far as the response time of the application goes. We assume that the virtual machines are essentially in hot standby, and they can be configured in the platform on the fly. So this is a first set of results that we obtained. We have a number of nodes which is very limited. It goes from 1 to 3 only in this first exercise. We set the response time to 200 milliseconds, and as you can see, there is a threshold. The green line indicates the threshold that when it's reached, when the response time goes over that threshold, more than 5% of the times, then the platform is reconfigured. And the threshold is below the actual response time negotiated in the SLA, because we maintain a margin just to guarantee that the SLA is not violated at all. So usually violating an SLA means penalties for and economic penalties for the provider. So in order to make sure that the SLA is not violated, and at the same time, in order to prevent the provider from doing over provision of resources, just to stick to the SLA, we use this threshold, which is just a little below the actual negotiated response time. As you can see, we use the load growing up to 90 requests per second, with an SLA limit of 100 requests per second. And the blue line that you see on this slide indicates when the virtual machines are allocated and released according to the load that is occurring is put on the application. This on the left-hand side graph. On this right-hand side diagram, you see the violation rate. And under this particular circumstances, you can see that the 5% SLA efficiency limit is maintained. It's always below the 5%. The violation rate is always below the 5%, which is admitted. Then we thought that this effectively the number of virtual machines that we were allocating is really very small. So we augmented the number of machines available up to 13, and maintaining the same requirements as before. That is the violation rate of 5% and below the 5%, and response time below the 200 milliseconds. Even in this case, you can see that the violation rate never goes above the 5%, which is expected, as expected, and the resources are added to the platform and released when necessary, as the load varies. Out of this exercise, we thought that these are just very initial results. As I said, we thought that they appear to us quite encouraging. That simply says that our design approach appears to be adequate. However, there are a number of problems that remain open that I think are interesting to investigate, and I'm quite happy I found in this workshop sort of confirmation that this some of the things that you see in these slides were actually written before yesterday, and I found that yesterday were confirmed by the presentations that I heard. One thing I wish to point out is that if we go for a dynamic configuration approach, then when we manage a large number, well, if we're going to manage a large number of virtual machines, we may hit a scalability problem, not necessarily in the platform, but in the collateral subsystems. So if the virtual machines share a database, say, the database itself might become a bottleneck if you have a large number of these machines. Of course, one can replicate the database and distribute the load across the database. But then you hit the problem of maintaining coherence in the database and amongst the various replicas. So I think this is a problem that deserves attention and further investigation. In addition, this observation that we made, and I guess we share, that the virtual machine allocation time can be very high and may lead to SLA violations. So this goes to say simply that it's necessary to investigate virtual machine management and allocation policies that can prevent from violating possible service level agreements. So we are planning to do further testing on of our architecture using real cloud as a test bed. One of the candidates is OpenNebula, which is a cloud in open source. But we hope that maybe after this workshop, even Microsoft Azure might become available for some experiments. One of the things we would like to look at is extend the range of quality of service requirements we wish to consider, and in particular we would like to address dependability requirements such as fault tolerance or security. I think that an analytical modeling of cloud computing environments and consequently of our architecture would be extremely useful to understand where and to invest in order to ameliorate and to make better progress in quality of service aware cloud computing environments. And we would like to look at both issues of cloud federations, and in that particular context, we think that will become particularly relevant issues of trust and trust management, and as it was pointed out yesterday, as well in one of the invited keynote presentations. We also think that the integration of cloud computing with mobile devices and services is one of these very challenging scenarios that is worth investigating. And that ends my talk.
Well, thank you very much for that interesting talk, including a lot of performance figures, which I think are important for all of us to know about. Questions? Yes?
In terms of scaling up and down your VM allocations, do you do this with increments of one machine at measurement points? And do you think it would be useful to do it more aggressively or with other...
What do you mean by more aggressively?
I mean, yeah, for example, if you get really large load spikes and you really need, let's say, more to increase the number of machines with more than one on a short term, so you can deal with the load. Is that something you're looking into, or?
Yes. And in fact, it is something that we did in the other project, and as part of the exercise we did before, and when we implemented the distributed application servers, we did augment the number of nodes that were brought into the platform in much larger numbers than that.
If I can just follow up one more question on that. So if you look at, for example, EC2 offerings, you have a lot of different instance types you can acquire. So are you also looking into performance modeling or workload modeling to kind of decide on what kind of machines you're
This is what we would like to do. As we find the people that can actually work on that, we're very happy to collaborate with them.
All right, you can take it on.
But indeed, I think it's one of the really interesting topics.
Other questions? Okay, great. Well, we'll thank our speaker then, and we're going on to the next talk, which is a change in the program. The next speaker is actually Sarunas Gadživakas from...
It's a very complicated name right now. Girdziauskas.
There you go. From Sweden. So if you want to switch around, now's your chance to move. Okay, welcome to the third speaker in this session on systems and infrastructure. We have Sarunas from the Swedish Institute of Computer Science in Stockholm, and he's going to talk to us about cognitive publish and subscribe for heterogeneous clouds. Over to you.
Thank you. So my talk will be a little bit different than what we heard before, because that's only the paper, current paper that we're working on in our institute with my PhD student Fatime Rahimian, who did the most of the work in simulating and experimenting with the system. So I'll be not that as broad, but we'll go a bit to the more specific problems of this cognitive publish-subscribe systems, which we use for heterogeneous clouds. Okay, so what is the future of the clouds? And although we saw this last 2 days that the future is for Microsoft, Amazon, Google, we have a bit of different thoughts. Maybe part of the future of the clouds will belong to the decentralized architecture, and it's maybe not that surprising, because imagine how many good computing devices we have with us, laptops, phones, iPads, whatever. And what's more important, they're getting better and better connected with each other. And that brings, like a new media of possibilities where we could come with our devices and to ask this cloud for resources, but also can contribute our idle resources to the cloud. So we think that in the future will be this network collection of connected devices forming various microclouds, which will be extremely heterogeneous with a different, very different computational capacities, different bandwidth lengths, different costs between them, and that we'll have to take into account. So one of the main building blocks for such a decentralized architecture is a publish-subscribe service. And this is very broad concept, you can imagine that the users would like to subscribe to their favorite TV channels for IPTV, or maybe scientists would like to subscribe to certain Large Hadron Collider data or some astronomy data. Or it's a very, very broad concept, but it has to work. And it has to, this whole system, if you want to embed it on top of this heterogeneous cloud, has to adapt to the topology, adapt to the existing connectivity to use the cheapest path. And not only that, it also has to be cognitive and to understand what are the user patterns. Because probably people or users who watch TV will have different patterns than scientists who are subscribing for some scientific data. So our focus is on the publish-subscribe system, which has a very large number of nodes, very large topics on which you could subscribe, and resides in the heterogeneous environments. And we assume basically we propose our solution to these cases where central solutions will not scale. Of course, there are many trade-offs to consider, and you can say, why not to simply make an overlay for every topic? If user wants to subscribe to a certain channel, go on. We make overlay for every user who is in this topic. However, in this case, we might be not very scalable, because with a growing number of interests per user, you will need to have unlimited bandwidth or unlimited neighbor set. And in this case, we might end up scaling badly. Other extreme is to simply flood or some kind of flood the events or the data through the system, but then we have a problem that there will be many relay nodes involved, which will not be able or will not want to cooperate, because remember that the amounts of data grow very fast, and if you have to relay some gigabytes of videos which you're not interested in, and especially if you might need to pay for your provider or something, you might be considering that. So we have to take into account these issues together with the dissemination delay, how fast you can get the notification when the publisher issues, and of course what is the cost to get it. And that's, I guess, most of the very important for the internet providers, because so far most of, I guess here as well, you pay flat rate for the users of internet, but the internet providers don't pay. They have actual costs assessed with each of their networks. So this also has to be taken into account. So we will try to make a cognitive publish-subscribe system which would have a fixed bandwidth, fixed node degree. We will not let it grow indefinitely. However, we would like to scale to any number of nodes or any number of topics, and to understand, basically to let the system in decentralized fashion without any global control to discover what is the underlying topology, to find the most cheap paths in terms of bandwidth and cost, and to minimize the number of these relay nodes using subscription correlation patterns, because it is known that users do tend to have correlated interests. If you look from the bigger perspective, the work that we've done is, if we see these heterogeneous clouds with this physical network with specific properties, we'll try to build on top of this cognitive overlay, which would take into account all these properties that we want, and then using the connectivity of this overlay, we would build efficient dissemination structures for each topic. And since we use only the links of this overlay, and this overlay will be scalable by definition, all the dissemination structures will be scalable as well. So how do we do it? We employ very nice gossiping technique for building these overlays. And for those who don't know, the gossip is just a very lightweight, robust, and scalable mechanism where peers talk to each other, talk to only their neighbors in the local vicinity, and exchange information about the world. Usually they exchange the view of their neighbors, and then this propagation spreads, and the peers can start forming different structures. So with this type of mechanism, we build our overlay, and it's maybe a bit more complicated than that, but in the nutshell, it works like this. A node starts with a simple view of the neighbors, like it has some arbitrary neighbor set, and it meets some other node. They exchange these views, they merge them together, and then this two-view set is ordered at each peer with their own preferences. And these preferences is the most important thing here, because we can use some kind of ranking function. If we want to do it to cluster peers with similar interests, a peer might rank the peers in a way that it would prefer peers with the most with the most similar interests, or maybe peers which have the cheapest connection to each other. And if we continue, if we repeat this, oh yeah, I forgot to tell, and once we have it, then every peer cuts this chunk of the new set with the limited basically neighbor set, the one that every peer assigns to itself. Basically, that's how we scale. And with repeating this process in very short round of steps, usually in logarithmic number of steps to the population size, we can converge to a very nice structures where we have clusters of these peers of these nodes which are similar to each other. In this way, when they're similar, then we can disseminate any events in these clusters very efficiently and cheaply. So just to illustrate, so say we have such type of network, and there are, say, peers interested in a red topic, and if we apply this gossiping in the background, and we have as a ranking function, we rank basically the peers with the function we have such a similarity metric, where we take, for example, a ratio between the intersection and union of the subscription sets between two peers. So in that way, if peers are have identical subscription, they will have similarity 1. If there is no subscription in common, then it will have 0. If there are some interest, it will be something between 0 and 1. And if every peer does it and leaves for itself only those neighbors with the highest similarity metric, they will eventually converge to the structure where, for example, the red nodes will form a cluster, the white nodes will form a cluster, maybe there will be some peers interested in green node, they will form a cluster. It might be that they won't form a cluster because they will not be similar enough, but we do our best with the local knowledge to cluster them. Not only that, we can also take into account the link cost. So for example, if this link is very expensive or starts to be very expensive, this background mechanism of gossiping can rewire it and point the green topic to point to the other peer, which is maybe cheaper. We can also, with the same mechanism, cluster peers not only by the link cost or intersimilarity, but also cluster only those topics, or prefer clustering those topics which have a very high publication rate, or they're very popular, because we would like to be more efficient for those topics which are expensive to or very popular, and those who are not that popular, maybe we can deal it somehow differently. And let's not forget that always we keep the degree of the graph, or basically the bandwidth for every peer, limited. So every peer can decide for itself, and we don't need to grow linearly with the number of topics that we're interested. Now there are problems with that, because we have this limited node degree, it will be inevitable that some clusters will be disjoint. They will be connected through some other peers, but just because of this, that we have a limit, they will be disjoint. And if we want to publish events on that, we will have to ask for the relay traffic for some other nodes, but we have to do it very carefully and to involve as few as possible of them. Now, how to do it? So that's basically at this point, most of the similar approaches stop because they either do it, either they cluster and then say that, well, you know, because of the correlation, we might expect that our bandwidth will not grow very high, but they don't give any guarantees. Others just involve many peers in between. Well, we do it a bit differently. And we, having this already made the graph, which there is a nice clustering phenomena inside, we embed it into the identifier space. And in that way, we make a navigation in this graph possible where any peer can find any other peer just by greedy routing. It's, we usually build a navigable small world network. For those who are interested, it's basically the work of Kleinberg, John Kleinberg, who first proposed it. What's even more nice that we do it with the same mechanism of gossiping. We don't employ any other new technique. We just change the, oh, sorry, I'll talk about this a bit later. But basically, for embedding structure, we change just apply a bit different ranking function for our gossiping technique. And once we have it, when we know how to navigate from any point to another point, then it's pretty, I'll show you, it will be pretty easy to connect these topics and to publish on them efficiently. So how do we build this navigable structure with the gossiping? We assign for every peer a random number, let's say some ID from some identifier space. It can be one-dimensional or several-dimensional, and adapt the ranking function in a way that it's not only chooses now the neighbors as with the similar interests or the cheap costs as I showed before, but also prefer, like for one or two links, prefer neighbors which have very similar ID to their own. And when you do it recursively, after several rounds, everyone is connected to the closest neighbor in terms of the ID, and in a sense make a ring. And it's not a very nice ring here; it's a bit twisted, but in general it is a ring, and a ring allows us to navigate from any node to another node. So we are for sure approaching the target. There are some other things to consider. We have to, in order to be more efficient, we can put this small world style fingers, but I will not go into details. We just say that with this type of technique, we can assure that the navigation in the network will be polylogarithmic in the size of network in the size of the population. So basically, we can build with this gossiping technique efficient navigation structure. And once we have all these now three types of links together, these friend links, let's say, which we cluster because of similarity, the ring links for the navigation, and the long-range links for the efficiency of reaching the neighbors, then it becomes pretty easy. We just say that let's assign for every topic some rendezvous node, and it's easy. You hash a topic name, and then you can get some ID from this identifier space that we use, and greedily route from every cluster to this rendezvous node, and upon routing, ask for every node that we traverse to be involved in publishing this topic. We don't create any new links. It's the same links which we basically, the same node degree doesn't change, but just in that way we can connect disconnected components, and we basically gain, we retain this clusterization phenomena in the system while being able to navigate and connect them. So, yeah.
Why the number 3 and number 5 is connected?
No, actually, it connects through this node.
Why that?
Well, it's okay. I don't know whether it's just for presentation purposes, but let's say if you route from number 3, and you say if number 3 knows that 5 is a rendezvous point, it would say, which is the closest neighbor of mine, 35, 28, 20, or maybe here was, I guess, some small number. And probably this small number is closest to 5. And when it comes here, then it says, okay, who is closest to 5? And it says, oh, I already have 5. And I come here. And every node does the same. So this 4 for example, also tries to go to 5, and it sees that 8 is the closest, goes here, and reaches the 5. That's the nice thing about navigable structure which you have. Because whenever you impose the graph into the identifier space, and if you create a correct connectivity, you can exploit this greedy routing. And greedy routing is basically minimizing the distance to the target. And if you know the target, you can reach it.
Right, but you need to know, you need to go to number 5 to get the connection.
So let's say red topic is disconnected, and red topic has some name. So if you devise a rule that every peer hashes a topic name, and you get as a hash value some kind of number, let's say in this case 5, and everyone does it. And everyone can do it independently. So everyone knows independently that for red topic, if you want to find it, you have to go through 5, to 5. And then at 5, they all meet. There are some peculiarities. I don't want to go to the more details because you can have several routes from every cluster in order to make more robust or how we find it. There are details, but in this short talk I cannot. If you want, we can talk it offline. But basically, we do account for all of it. So in this case, all the topics become connected, and then we can simply flood within this topic any event, and then we are assured that we will involve only the topics that are interested and few other nodes which it is inevitable to involve in order to connect these joint components. So since it is ongoing work, we don't have the full results so far, but if you're interested, I have some graphs. But the first experiments are really promising. We were working with many synthetic data sets, which are actually, there are quite a little bit of a work on how to synthesize the user subscription patterns, which methods to use. We also we crawl the Twitter data set and use the graph there where which people follow which one, and by that we induce what kind of subscription correlation is embedded there. For a churn, we use there is a Skype churn data available on the internet, and our experiments show that in some cases, if you compare to the existing approaches like Scribe or Bayux, if you know those that do have limited basically node degree, but they don't take into account the underlying network, underlying sort of similarity of the peers, and we have even up to 10-fold increase of basically reduction of relay traffic. We involve much less number of nodes, and if you think that if this would translate to some gigabytes of data that you have to transfer, this big, it can be a very big savings. So to wrap up, we are working on this large-scale PubSub for heterogeneous environments, and the main idea is to make this cognitive overlay where we form the clusters of similar nodes in a decentralized fashion using gossiping, and by doing that, this overlay eventually goes through this, makes the most efficient paths that exist in the network. So it could be very nice for the internet providers. Basically, if they throw this system, and if you can somehow measure the cost for every link, they would converge to the least expensive path to disseminate the data. And of course, since this gossiping is always running on the background, whenever anything changes, if there is environment change, we can always adapt and make new connectivity. And we show that it is very fast convergence, and the experiment showed it's pretty robust to churn and failures. So with that, I finish, and thank you very much. I'll be happy to take some questions.
Well, thank you very much for that most unusual talk. And are there questions? Yeah, two there. You first, yeah?
I'm a little bit confused about your gossiping. If you look into the routing literature of wireless internet networks, usually gossiping doesn't guarantee delivery of information. because somebody who got the gossip can discard this information. How do you deal with that in
Well,
work?
So actually, that's why we build this structured overlay on top of gossiping, in a sense. With gossiping, we actually build a structure. And even if you...
How do you build a structure if you are not under control? You have a distributed system.
You mean that there can be peers which maliciously drop the packets? Oh, well, okay, this at the moment we don't deal with that. So, I mean, I think this is pretty orthogonal research which has to deal with there is a lot of in the peer-to-peer community research on how to isolate, how to overcome the peers which decide not to conform to the existing rules. So in this respect, we assume that the nodes will play according to the rules. And yeah, if you want to implement it into the real life, of course, we would need to take care of all these issues.
I have a second question.
Yes,
possible. What's your greedy function? You have some greedy routing implemented on
Yeah, so it's just minimize. So if once you have the identifier space, when every node has a
distance.
Yeah, exactly. So that's in that case is you minimize the distance between the identifiers in a sense.
There was a question here.
Yeah. So when you build the overlay structure, is that a static structure or it's a dynamic structure? When there are more subscriptions come in, the structure may be changed, or it's a fixed structure.
So exactly, if nothing changes in the system, if the costs are the same, if the peers don't change their interest patterns or interests, then eventually it will converge and will stay the same. But if somebody at any moment in time can say, okay, I'm not interested in this topic anymore, or I am interested there, or there is a new connectivity, a provider installs a new fiber and then it's cheaper somewhere, then the structure will change, adapt, and again converge to some state. Of course, in the reality, everything changes all the time, so you always adapt. That's why it's adaptive.
Okay, well, I think we must stop there because our last speaker is ready and poised.